So I'll now start a presentation about factors, mainly focused on the work that, as Vera said, the work we did on the user-focused Marinium project. And I also give some background about factors and how to use factors in Marinium so that you get all the needed knowledge for the tutorial that we have prepared for you. So in this project, Bubble had two main activities. The first one was the actual implementation of factor translation in Marian. And we had a second activity where we used that factor implementation for forced translation specific for terminology. I'll describe, as I said, both our contributions in these two activities. And finally, we will have a tutorial where you can hands-on play with a factor scope. So let's start by giving a background regarding what is indeed factors. So factors are a mechanism by which words are represented as a bundle of features. Imagine that you have the word Lisbon, for example. You could divide the word representation between the word Lisbon, but lowercase. And if for some reason you want to encode the casing information into a factor, you would have not only the token Lisbon, but also another token that would be a capital C that would indicate that that word was a capital word. We could also use other factor to say that Lisbon is a noun, for example. To the first factor, to the word, we always call it lemma. And to the remaining factors, we call simply factors. Another important topic that you need to be aware of that you probably are at this point are what are word embeddings. And word embeddings are simply a representation of words into numerical vectors. It's a process to turn the words into these numerical vectors because we all know neural networks understand numbers, not words, right? So how does this process happen? Usually you have what you also probably know already, a vocabulary where you have basically the list of all the words in the language you are translating into or from. And then you represent each word by a vector, what we call, with a method that we call one-hot encoding, which is basically you have an array full of zeros, and then you have only the number one in one spot of that array, which is the spot that corresponds to the word that you're trying to encode. So in this example, you can see that Lisbon is the third word on the vocabulary, so you see that the third spot on the array is the one. We then have what we call an embedding matrix, and when you multiply the one-hot encoding vector by the embedding matrix, you will get the numerical array at the end, which is the word embeddings. But when we are using factors, one big question arises, which is how do I combine the word embeddings and the factor embeddings? And that's exactly what our work was about. So how do we combine the word and the factor embeddings? So we implemented a new way of combining the words and the factor embeddings in Marian, which was by concatenation, because first Marian already have some code there, but it was only allowed us to do it by sum. Another thing that we did in the project to Marian was we make the factor implementation more user-friendly because, as I said, some code was already there before we started working on it, where it was kind of experimental and not that user-friendly and not that well documented. So we also documented heavily the code. And we wrote the documentation that we linked in the Marian Dev repo. So how the factor embeddings happened in Marian before we started working on them? So as I said, it only was possible with sum. So remember that I mentioned the one-hot encoding vector. So when you are using factors, actually you can have a multi-hot encoding, where instead of having only the number one appearing once, you have a number for the word and a number for the number of vectors that we have. And then when you multiply it, you can see here that we represented in blue, we have the word embeddings, and for the factor embeddings, we have these two matrices concatenated by the rows, the red one and the yellow one. When you multiply the multi-hot encoding matrix with the word and factor embedding matrix, you will end up to have the word embeddings, and as you can see, when you multiply this matrix by this matrix, all of the embeddings of the word and the factors will end up being sum. This has two main drawbacks, which are the first one is that, of course, you can always combine embeddings by sum. You could want to use concatenation or averaging, and you can with this method. And also, with this method, all the factor embeddings end up to have the same dimension as the word embeddings. And usually the vocabulary of factors is much smaller than the words. For words, you could have a vocabulary of size 40K, and for factors, usually you have, for example, the example that I gave for capitalization, you have only 3-4 possibilities, right? So the one vocabulary is much smaller than the other, so it doesn't make sense to have such a large encoding dimension for the factors. So what we did was we changed things a little bit. We start by simply embedding the lemmas without the factors, and separately, using the multi-hot encoding technique that I presented before, we only use it for the factors. But since these two steps are now separated, later we can combine the embedding metrics as you want, and you can see here, now we have a dimension specific for the lemma, one dimension specific for the factors, and now you can specify this in the command line interface when you start the program. So, all these that I taught now were for source factors, so factors on the source language, but Marian also allows us to have factors on the target language. So it allows us to predict not only the word, but also the factors. And as you know, so when you are decoding, at each timestamp, usually you make a prediction, a word. So in this case, Y1. But when you have factors, as I said, you also need to predict all the factors. Usually, the most common method to do this is that so you have the last hidden state that your network outputs, here represented by HT, and as you're probably aware, in a common neural network, we have the output embedding matrix, and then you have the predicted word, right? But when you want to predict a factor, probably you also want to make that factor prediction based on what you predict for the lemma. So what it is usually done is that you grab the hidden state, you reproject the word that you just predicted, and you use that new output embedding to predict the factor. So as you can see here, the factor Y2 is being predicted, taking into consideration what we already predicted as the word. So the factor has a dependency on the lemma. And how does Marian actually outputs the factors? So predicts the factors. So Marian has in fact 3 different methods. It starts always by predicting the lemma, as I explained here. So the first step is the same for all the 3 steps that I will present. The difference is how Marian makes the factor dependent on the lemma. So the first thing that they are implemented there is something similar to a transformer layer, where you basically use the lemma and the factors to populate the query keys and values, and you use the attention matrices for a typical transformer decoded layer to also output the factors. The second method, it's what we call the lemma custom projection, which is basically this common method that I explained before. And Marian also has the lemma-dependent bias, which is really similar to this one. The difference is that when you reproject the lemma to use that reprojection to output the factor, actually we reproject to a one-dimensional array, and you use that dependency as an extra bias to output the factor. Let's now go to the fun part, which is how also all this translates into results and to the experiments. So the first experiment that we did was for applying factors for terminology. And in this experiment, we used it to compare the method that was already implemented in Marian, which was summing, and the one that we implemented, concatenation. We only used source factors, and the main goal of this experiment was to use factors to increase the terminology rate, but not degrade the overall MT quality. So how did we use factors for terminology? Imagine that we have this sentence that wing as a winglet, and you want to translate it to German. Winglet is a really specific term, so the system might get some problems translating it. So what we did was the following. We added to the source text the target word that we wanted to translate, and then we used factors to give meaning to each one of the tokens. We used P0 for words that were already part of the source sentence. We used P1 for the source version of the term that we want to force translate, and we used P2 for the target version of that term. And hopefully, after training, we hope that the system learns that every time it sees a word marked with a P2 after a word marked with a P1, it knows that to translate a word marked with a P1, it should choose the word that we added to the target marked with a P2. And now, this translates into results. So we tested this for 4 language pairs, English to German, Latvian, Norwegian, and Romanian. And you can see that for all of them, the terminology, the accuracy rate increased by 10-15%, and that our method, concatenation, in the dark blue bar, actually gave extra improvement on these results. And as you can see on the blue scores, the overall MT quality was not degraded and became constant. So we fulfill our objective of increasing the terminology rate without degrading the overall quality. On the target side, we also used factors. So to test factors on the target side, we use them to encode subword splits. So you probably are all aware of this VPE, where you split words into subwords. And what it did was, instead of encoding the subword with the at, we decided to encode it with factors. So we had two possible factors, GF and GT. Basically, they indicated that if a token had the factor GT associated to it, it should be joined to the token before on the sentence. And yeah, of course, that in this experiment we use, as I said, factors on the source and the target. Regarding results, they were actually a bit underwhelming. For German, we actually got a slight increase in terms of the quality of the translations, but for all the other three, the quality decreased a little bit. Although you might argue that we have some advantages of doing this, because since now you don't have, for example, the word study at, and you only have the word study, your vocabulary decreases, which might be one advantage for some applications. But the good thing about this experiment was also that we were able to benchmark all that target prediction methods that I mentioned before. And by this table, you can see that using target factors actually decreases a little bit the training speed and decoding speed, which makes sense because you are adding a lot of extra trainable parameters to the neural network. The one that gave the best results in terms of quality was a soft transformer layer, although it is the slowest because it's the one that has more trainable parameters. And we found out that the lemma-dependent bias seems to be one that has a good benefit rate between what we lose of speed and what we gain in quality. The second activity of Unbubble was related to forced translation. So since factors were already implemented and they were stable, we used it to improve a little bit the terminology experiment. We based our work a lot in a paper from Tilda, also a partner in this project. And the idea here was, now we not only want to translate the terminology, but we want to correctly translate it and inflect it. And how did we do this? So this is really similar to what we did based on the Amazon paper that I presented before, but with a small difference, which is, imagine that I have this sentence, I bought 2 books, which translates to Portuguese into eu comprei 2 livros. And what we did was the following. We lemmatized the target words on the training corpus. So you can see that the verb now is in the infinitive form and livros is in the singular form. Then we use alignments to align the source words and the target lemmas. And what we did was annotate we chose randomly nouns and verbs, and we annotated the lemma on the source. So what we want here now, as you can see, is we not only want that a neural network learns that each time it sees a P1, it properly translates what we mark with a P2, but also that knows the inflection. So now we do not here to teach only copy, but we want to teach copy and inflection. And what did we got in terms of results? So you can see that the terminology rate was heavily increased. These test sets are domain specific. For German and Latvian is domain specific to industry and mechanics, and for Norwegian is politics and medicine, and for Romanian is politics. So the test set is really specific to a certain domain, which is where terminology plays a key role. And regarding the overall quality, we can see that we got a huge increase in German to Latvian, and we did integrate it in Norwegian and Romanian. But as I mentioned, we wanted here not only to properly translate the terminology, but also correctly inflect it. And automatic metrics do not detect this that well. So we also relied in human evaluation. We asked 2 questions to the annotators. The first one, which translation is better overall? As you can see, for Norwegian and Romanian, both systems were competed more or less on the same step, but for German and Latvian, we actually got a bigger answers positive for the factor model. Then we asked a second question, which was, now looking only at the terminology, tell me if that term in the sentence was properly corrected and properly inflected. And here, what you can see is the percentage of times that the annotator said that in the corpus, the words were properly translated and inflected. And you can see that the factor model overperforms the baseline by far for all the language pairs. So to conclude my presentation, with these results, we can see that factors are indeed a powerful tool to encode meta information about words or phrases in an MT system. We did it for terminology and BPE, as you saw. Using factors in Marian is now so much easier and is ready to use for everyone that wants to use Marian. And on a side note, factors, we also experimented factors for other purposes. One of them was to encode morphological information, and we have also some results on these on the appendix if anyone is interested about them. Finally, another good use case for factors is replacing factors to use the true case, so encode capitalization in factors. And good news, that's exactly what you are going to do today. So now I will pass the word to Christine, which is going to guide you through our awesome tutorial about using factors for replacing the true case. Yeah, thank you.
Okay, thanks, Pedro. So yeah, now we're getting into the hands-on tutorial part where we'll actually train a tiny factored NMT model. Probably you won't train the whole thing now, but we also provided some pre-trained models if you just want to test the decoding part. Okay, yeah, so I'll just kind of quickly describe the task in this tutorial. And as I said, if you want to just kind of read ahead on your own and try things, hopefully you're set up on the machine, but it's designed to be able to run on your own machines as well. GPU is better, but it should also work with CPU. Okay, as Pedro said, the task here is to use factors to encode casing information of words and subwords. So here's a little example of the pre-processing that needs to happen for Marian to be able to recognize these factors. And basically what you do is you separate each word or lemma and its factor with a pipe. So every lemma gets its own factor. And the ones we've chosen here are C0 through C3, where C0 represents an all lowercase word, C1 represents a title case word, so like just the first letter is capitalized, C2 is all uppercase, and then finally C3 is just like other stuff. This like probably isn't like the best way we could have done it, but this is just an example, so these are the ones we went with. So yeah, all of the scripts in this repository should let you train this thing end to end. And there's two versions of it, one with only source side factors, and then one where you have source and target factors. So in addition to predicting target lemmas, you're also predicting factors, and then you post-process to re-include the casing information. So the data set, it should already be downloaded when you clone, but it's like just the news commentary for German to English. I think it's around 200,000 sentences. So there's just a few requirements. You need Python 3, you need Marian, obviously, and this repo. So to get started, you need, well, you don't need, but we recommend creating a Python virtual environment and then installing the requirements there. It's just a few things like SacBlue and subword NMT. And then finally, there's one more dependency, which if you just run that script, install dependencies, it'll download the Moses scripts for you, which we're using for tokenization. Okay, and then you need to set up this .env file. Most of it is already ready to go, but just some notes. In the experiment, you can either choose to run the source factors only experiment or source and target factors. So changing that controls which one you're running. You also need to put the path to the Marian dev build folder. I believe that should be in the Slack somewhere, but I think it's opt Marian. And that is it for the env. I think we might need to change like the GPU device.
They don't need to change the GPU because they're all assigned to a random GPU, and Marian is /opt/Marian if you're on the cloud or wherever you compiled it.
Thanks. Okay, so that should all work. Here we have the factor prefix as C. You can change it, but like you don't have to. And then, yeah, okay, so the last thing is this like model directory. When you're running training, you can just leave it as what it is now. But if you get to training and it's like taking forever and you want to kill it and just see what decoding's like, you can switch to this path instead. And we provided some models we trained earlier, so you can see how decoding works. Yeah, and then just with the data, it should already be there in both directories, split into test, valid, and train. But if you want to see how we prepared it, there's also a script for that. And then that is it. So to get more details on each part, we can go to the directory for the experiments. And each one, well, there's one script run end to end. So if you run that, it should just do everything. But for the sake of learning, probably it's better to just look in that one and then run the scripts individually and see what the outputs are. Okay, so I can talk a little bit about the source factors experiment. Like I said, you have to set the experiment in your .env. You can just run it, but probably it's better to run one at a time. So the first thing that happens is pre-processing. It'll run tokenization, like very standard. Here, there's like a factor specific step, which is escaping of special characters. Because these characters like are meaningful to the factored vocabulary format. So if you have these in your vocabulary, it'll get messed up. So we just do like a really small like little replace with these, and then we de-escape them at the end. Okay, then you basically add a factor to each token. So there's like a script that does that. You can look at the details, but it's like fairly straightforward. If it's capitalized, it gets C1. If it's like all caps, it's C2, and blah, blah, blah. Okay, and then here we do like a little trick, sort of, to be able to run BPE on the unfactored corpus, but then apply a words factor to each of its subwords. So what we do is we, after we add all the factors to the tokens, we then create another file which has all the same tokens but without the factors, apply BPE on that, and then there's another script that adds the factors back to the BPE subtokens, subwords, based on the original factors. That was like kind of confusing for me to explain, but I think once you see the outputs of the scripts, it'll make sense. And then finally, there are some like tricks with the vocabulary. Yeah, Marion expects a special format for factored vocabularies called .fsv. I can show you kind of in the original documentation we wrote. Yeah, and this README in general is like really good for a lot of factors details. It's linked all over the place in our tutorial, so we recommend that you read this also. But basically the factor vocabulary has a few like sections. So there's the top section where you kind of define each factor group. So a factor group is like both the lemma and then what we're calling has C, the like capitalization factor. But if you had more factor groups, you would add them here. And then it's just like a little bit of like syntax to say which factors belong to which factor group. And then finally, you add all of like the actual words or the lemmas, and you say which factor group each one belongs to. So yeah, that's that. You create the FSV with our scripts. And for using only source factors, you can pass Marion the factored vocabulary as a source vocabulary, and then the regular like YAML or whatever as the target vocab. So that's like a little overview of pre-processing. For training, Again, we have the script that should just do everything, but a few comments. Yeah, as I said, like the vocab, you can put the FSV on one side and then the YAML on the other. We're running with tied embeddings, and again, there's like a few tricks for this. So if you're only using source factors, you have to use the concatenation option, or you can kind of do it with like fake factors. So if you want more details on that, again, it's in like the main README. Yeah, there's like a whole section on weight tying. And then, yeah, we're also using, as I said, concatenation, and the factor embedding size is 8. Okay, so if you're running the end-to-end script, it should have run pre-process train, valid, and then the actual training part. And if you get up to that, probably training the model takes a few hours, so you won't have time. But after it gets to like a few epochs and validates correctly, you can just kill it if you want, and then continue with this inference section. So what you need to do here is change the model path to this pre-trained model. If you continue running end-to-end, then it'll pre-process test. It'll run inference with the translation. And then finally, it will post-process like the usual stuff, including the escaping of these characters. And that's pretty much it. It'll run Sacreblue, and we got around 32, but you might get something slightly different. I don't know if anyone has questions so far, or I can just kind of start running it and people can watch. I don't know what everybody wants to do.
There's nothing on the chat so far.
Okay. Well, maybe I'll just say like a few words about the source and target factors experiment. Just highlight what's different. So yeah, okay. Pre-processing is mostly the same, but of course you also have to apply the factor steps to the target side as well. And then you have the target vocabulary also as an FSV. Yeah, and if you're tying, or sorry, if it's like a joint vocab, you can just use the same file. So that's kind of it for pre-processing. For training, yeah, you use the same vocab, and then tied embeddings also works because we're summing. Yeah, okay, so for this one we're summing. And as Pedro mentioned, there's different options for predicting the factors based on the predicted lemmas. And the one we're choosing is the soft transformer layer, which was like the best one, but really you can use any of them. And if speed's not like a consideration, you can pick the other ones. Yeah, and that is like pretty much it for this. Yeah, the post-processing is the same, except based on the predicted factor, you recase the text. And yeah, I should have said in both of these experiments, we kind of have like usage guides on each of the scripts that we wrote. And I think that's it. Okay, so I think I'll just share my terminal and start running things. But like really just feel free to stop me if you have questions. Okay. So I already cloned it here, and now I'll just start installing the dependencies and stuff. updating the end file. That's the right path. If it's not, I'll find out.
I think it's on with Mary.
Just Marion.
I think so.
Okay, sorry about that. So we've set up the end. And now, okay, let's see what's in the run end, and we'll just start running one at a time. So first we want to pre-process train. Oops. Okay, this is going to take a little while, but once it's finished, I can show you all of the different outputs. So the pre-processing finished. Let's now look at all the files. Okay, so we started with train. This is just the raw like German text. Nothing really special about it. And then the next thing that happened was the tokenization. And this was just from Moses Tokenizer. So also fairly straightforward if you're familiar with MT. Here we should also have those special characters escaped. So yeah, here you can already see one. We can't use colons, so we have this CLN. 1 second. Where was I? Okay, yeah, we have these escaped characters also in this file. That's it for that. And then the next one is the factored file. So here, every token in the previous file gets a factor. So you can see like the beginning of every sentence is typically C1, which is the title case factor. Like names, I guess, like Johnson also got C1. Most words get C0, punctuation gets C3. I guess because it's German, like the nouns are also like title case typically, so those ones are C1. Let me see if I can find a C2. Yeah, so I think certain like organizations, IWF, like WTO, those are typically all capitalized, so those are C2, same with the UN and USA. Okay. And then after that factored file is created, we then have the same like tokens, but with the factors removed. So you'll see like everything's lowercase because that's the version that has the factors applied, but it's just like all the tokens now without the factors. Yeah, so in practice, that file that I just showed is the same as the original tokenized file, but lowercase. Okay, and then we apply BPE to this file, the no factor file. So we don't have like the factors messing up like our subwords. Here you can see BPE was applied, the different subword splits. Nothing really remarkable here, I think. And then finally, the factors are like kind of like projected, let's say, onto the BPE subwords. So the final one is factors and BPE. Yeah, so let me see if I can find an example of where something was split and it has like each subword gets the original factor. Okay, yeah, I think here's one. I don't know this word because I don't know German. But I guess it was title case originally, the whole thing, and now each of the factors, sorry, each of the subword gets the same C1 factor. So this one here, and I think this is the last one. Yeah, and like feel free to take a look at the scripts and see how we're doing it. You might come up with a more efficient way. This is just what we have for the tutorial. And yeah, so just looking at like the target side, everything will kind of be plain. Yeah, so this is the English. You'll see that there's like no casing handling here, no true casing, no anything. It's just like the original one. But it's also tokenized and BPE'd. Okay, so I think now we're ready to train. We have to pre-process the valid set too. Okay. So I'll just pull out this command. Okay, yeah, and everything should kind of be the same as the training there. Right, okay, so training. Let's just like take a look at the command inside the file. Okay. So yeah, I mean, I highlighted some of these options. Sorry, when I was describing all of like the readmes, but you can see all of the options here that we're using. And yeah, it's using the factored BPE on the source and the just like regular BPE on the target. The vocabs also factored on the source and not on the target. And yeah, okay, let's see what happens when we train. Oops, I said copy. Yeah, okay, so we'll just let it train for a little bit until it gets through a few validation steps, and then I'll come back. Okay, so it got through one validation. The blue's like really low because it doesn't know what it's doing yet. So I think we're just gonna wait like another one or another two, and then we'll show you how the inference part works. But feel free to ask any questions or put questions in the chat. Let us know how it's going. Yeah.
There are no questions in the chat, but feel free just to let us know if you are following everything. Already a question. So someone is asking, what's the basic advantage of calculating factors over the word embeddings?
I'm not 100% sure what you mean by calculating factors. So it's actually using the factors? What? I'm not sure if I understood the question.
So can Farhan Dahani, sorry if I mispronounced your name, can you elaborate, or if you want to unmute and ask your question directly?
Yes. So how this approach of factoring is different from normal word embeddings?
Like the embedding process?
Yes, yes.
Yeah, so the basic thing that differs is that you actually, so the embedding process of the lemmas and the embedding process of the factors is pretty similar. So the way you embed factors is the same way you embed the words, the lemmas, so the proper words. The question that arises here is that how you actually combine them. And basically you have different options, and as I showed in the presentation, Marion already had summing implemented, but it has its limitations, and then we implemented concatenation. So yeah, the big difference is mainly the way you combine each one of the embeddings and not exactly the embedding process. I don't know if I answered your question.
Okay. Okay. So in this process, the similar words will be grouped together like they do in word embeddings.
Yes. So the embeddings, when you learn the embeddings, yeah, the embedding itself, ideally it will be similar for similar words. And then also good thing about word embeddings that I remember since you pointed that is that remember that in the BPE, when we encoded BPE as factors, we instead of having the word study and the word study at, if you encode the at as a factor, you only have the word study, right? So study and study at, that would have two different embeddings. If you encode BPE in factors, actually study becomes it only appears as study in the corpus, so study always is encoded the same way. If you use, for example, morphology into factors, since all the verbs, imagine that you use factors to say the verb and the tense and the person, the verb will only appear in the corpus in the infinitive form, so all the verbs will be encoded the same way, that specific verb. So yeah, you can also use factors to gain this advantage of words that have the similar representation and are not encoded the same way. With factors, they can be encoded in the same way, because you only have one representation of that.
Okay. Okay. Got it. Thanks.
Okay, thank you.
Okay, so if you're still watching my screen, it's gone for a few validations and we're getting above 0 blue. So we know it's starting to train. And yeah, the full training process will probably take, at least on the GPUs we used, I think it took like 2 or 3 hours. So this might be a little more, a little less. Yeah, and if you're interested in training like the full model, this is also one of the project proposals, kind of starting from here and making it better. So if that's interesting to you, come check out the other project related to this. So I'm just going to stop it and then show you the decoding part. Okay, so to do that, we're going to change the model directory to the pre-trained one. Okay, and first, let's see, we need to pre-process the test. Where's this too? Okay, and then we should be able to translate. It looks like it's doing something. And if you're curious kind of about the parameters and stuff we used, I mean, they should be exactly the same as the ones that were in the training script. But you can also see like the information here, and we also provided the training log in the same folder as well. Okay, so it's translated. And the last step, I believe, is to just run blue.
Post-process.
Right, sorry, post-process. And then I'll walk through like the outputs of all of these once we finish running the commands. Okay, yeah, and the blue we got here was 37.8. Yeah, so if you finish training the model yourself, you should get similar scores. Okay, let's take a quick look at the data. So we have the outputs of the model for the test set. This will be, okay. Okay, yeah, it's just a hypothesis file. So yeah, I mean, there's like not much to really say about this. But yeah, we can like maybe pay attention to the capitalization. So let me just look at the fully post-processed one. So that's without BPE and without tokenization. So I mean, it looks like pretty good. It knows to capitalize US and EU. I guess this is someone's name, so it knows to capitalize the first letter. GBP is also full caps. The first letter of every sentence also seems to be capitalized. Let's just see if there's anything that looks weird. Okay, these like apostrophe S's came out a little weird. That's probably something in the tokenization post-processing that we could improve. Like, yeah, like this looks good. This also looks good. Let me see if I can find something bad. I'm not sure I can find something right now, but imagine if you had a word like iPhone, it probably would not, well, I know it would not know what to do with that. It would either just come out like all lowercase or all uppercase or something. So that is like one drawback of this method. Yeah. Okay, so that's it for the first experiment that we provided in the tutorial. I can go through the other one because we have like 30 minutes left, but really like if you want me to re-explain something or if you have any other questions, really feel free to ask.
There's one question in the chat. Oh, two actually. So the first one, can we do away with Moses scripts plus subwords NMT altogether and use sentence pieces?
I would think so. We haven't tried using sentence piece with the factors. But that's definitely something we could try in the project part later on.
Yeah, just to add something that the thing that I'm not sure, but I think you would not be able to do it is use the sentence piece from Marian. I believe there is no support to use the sentence piece that Marian has inside and factors, but you can always use it before training. You just needed to make sure that the last step is the one that adds the factors the way Christine explained with the Python. So.
Another question, do you have any experience using factor segmenter from Microsoft?
I don't
think
check.
so.
What is a factor segment?
So there's an explanation added to the question. So it is a wrapper around sentence piece that uses factors for casing, making subwords and few other useful features, and it directly produces .fsv dictionaries. And earlier they used BPE and custom scripts for casing factors that were very similar to what you are presenting now. But for them, the factor segmenters seemed a bit easier to use.
Okay, yeah, this is cool. I don't think we've tried using this specifically. I guess like if you want to do kind of these standard things like capitalization and subwords and whatever, probably this is a good option. I'm not sure when this was written, but I would think it would still work with our implementation of the concatenation stuff. But I think if you want to do other, like use factors for other things, like the terminology stuff Pedro described, probably you kind of need to create all of the files yourself. Yeah, that's what I think.
Any more questions? Another one. It looks like models are overwritten if training is run and model directory is set to pre-train model directory.
Yeah, that's actually a Marian feature. So if you train a model, and if you are training your model, you should have in the .env change it to models, because as Marian works, the default settings is if you set a folder that does already have the model there, it will overwrite the model unless you specify. You need to. I think the setting is overwrite, the -- overwrite. You need to set it to false. But yeah, if you have in the .env the pre-trained folder set it will overwrite because that's the default in Marian. But you can always clone it again to a separate folder to have the pre-trained model if you want.
Yeah. So
yeah, as Kenneth said, yeah, it's not a bug, it's a feature.
yeah, so if you're training, use the other models directory, not the pre-trained one. Okay, I guess I'll keep going. So let's set up the end for the second experiment. Source and target factors. Yeah, and then we have to change this back to normals. Okay, so I'm just going to run the pre-processing. Okay, so the pre-processing finished. We'll just look at the data again quickly. Most of it will be the same as the source factors one. Yeah, so I guess now we can kind of look at like the target side more closely because this one will have factors. So let's look first at this. So it's basically the same as what we saw with German, where every token has a factor based on its capitalization. Then right, it gets removed before we do the VPE, and then it gets put back on the VPE subwords. So it'll be just this. Yeah, and again, it's the same, like where you have things split, split into subwords, they get extended to each subword. So like here also, there's this general skull something. Yeah, and that's that. And we also have so we created both the FSV and the YAML vocab, but we just need like the FSV for this training. So that is the data. And I'm just gonna quickly pre-process the valid and start the training again. Okay, yeah, and then if you look at kind of like the log, it has both factored vocabs. The factor settings are using some, and is that everything I wanted to find out? I think so. No, right, the lemma dependency. So for predicting the factors, it's just using the soft transformer layer for the factor predictions based on the lemma predictions. And yeah, so we'll just let it train again for a little bit. And then we should be just in time to show the inference with the retrained model for the system.
Just a heads up, Christine, we have 15 minutes left for this session, okay?
Okay, thank you.
Yeah, please.
All right, for the sake of time, I'm just gonna kill it and do the decoding. So okay, we need to pre-process. Yeah, I think this might be because we were having problems with the Git LFS. Or, oh no, it's because I didn't change this. Oops.
Oh, yeah.
It looks like it's working.
Yeah, just said it on the bottom.
So while this is finishing, are there any more questions we can answer? And also feel free to just keep posting in our Slack channel too, and we can answer questions throughout the hackathon.
So we still have 4 minutes left. Are there any other questions anyone wants to ask? Okay, so even if there are no more questions, you can also use the Slack channel to just post the progresses and let Christine and Pedro know if you are able to follow up and if you have any other questions or doubts.
Thanks, Vera.
Uh,
Oh, can I finish up?
yes, of course, of course.
So I think because I'm sharing a GPU, it's kind of taking a while. Oh, maybe it's working. But anyway, I think I have the files like on our own machine, so I can show you the outputs. Yeah, it looks like it would be here. So let's see. Okay, yeah, so now you can see the predictions also include the factors as well. If you look at the post-processed files, let's see. Yeah. You can see how we recased it based on the factors. Again, like certain like organizations are being capitalized correctly. Proper nouns also seem to be. But again, if you have a word like iPhone, it probably won't come out right. And so, okay, we didn't get a chance to run Blue on the other machine, but yeah, on this one, okay, I think this might be on slightly different data, but the mean score was also like around 32. Yeah, I think that's it.
Okay.
Thanks,
Yeah,
Vera.
go ahead. Go ahead.
That's it, I'm done.
Okay, so before everyone leaves, I just want to reinforce that there is the Slack channel for factored MT, so feel free to post anything there. And we are going to have now a short break, a 1 hour break, and we will be back at 1 p.m. for another tutorial on efficient MT. So I hope to see you all there. And thanks a lot, Christine and Pedro, and thanks a lot to everyone who attended the session.
Thanks.